大家好，这个是我们今天第二段的物数的影片，那就希望大家如果有回来的话，目前只知道有2位同学回来了，太恐怖了，所以我只是针对2位同学在上课吗 ？OK，那接下来的话呢，我们会讲 central limit theorem 中央极限定理，那它其实非常非常好玩，也非常非常有用。那同样的，到最后的话，我会留一个大的谜团，就让大家一起可以去解谜这样。So are you ready for this exciting ride? So let's begin. Okay, so this is the main slide of this video, and if you understand the full content of what these figure means, then you should be okay. So my job is to try to walk you through with all these interesting materials. Okay, before we move on to the technical part, let me check whether our broadcasting is correct. Okay, that's a little bit weird. Okay. So we got 4%. I guess that's probably fine. So I probably don't need to worry. So let's go back to our materials. Okay. So what exactly is central limit theorem? Sometimes you will find a very introductory article explaining the central limit theorem, but you find some misconception there. So hopefully I would like to walk you through in a more rigorous way and what exactly this means. So it's not like every single thing that you can always apply central limit theorem. It has its limitation. Okay? So first of all, you can see here, if you start from a normal distribution, a uniform distribution, an exponential distribution, or a log normal distribution that I didn't tell you, but if you just repeat these random variables many times and ask yourself, if I only care about simple means, and I will explain, okay? I will explain what do I mean by simple means later on. And it is surprising that you always end up with normal distributions. That is, no matter what kinds of distribution function you start with, you always end up normal distributions. And there is a tautological problem, right? If this is so true, and probability is about making the measurements many times, then why should we have any other distribution at all? That everything should be normal distribution, right? So apparently, that's not the meaning of central limit theorems. So let's start with just from 1. So if our first video clip is about one random variables, then this is about many random variables. So let's start with 2 random variables. So what we need is a joint probability distribution. So suppose now we have 2 random variables, x and y. How can we describe that? Well, you then face with a more difficult problems. You might assign a region A or region B that x, the random variable, occurs in A and y occurs in B. And you're asking what is the probability of that. And there exists a probability density function depends on x and y, and you just integrate over the corresponding region, and then you will get the probability. And as you see here, once you know how to define the probability correctly, it applies, right? So this definition here looks very similar to how we define the continuous random variables. So the discrete one for the joint probability distribution is easier, so I didn't explain them here. You're basically replacing this integral by discrete sum. Okay, and what about the cumulative probability function is also simple. For this, we can then introduce the bounds of a and b for x and y, and asking what is the probability for the random variable x is smaller than a and the random variable y, which is smaller than b. And this amounts to a double integral from minus infinity to a and minus infinity to b, and then you just integrate it over this whole thing. And one can ask yourself, just like before, when you have only one parameter, right? So the relationship between the cumulative probability function and the probability function is simple. You're just taking the derivative. But right now, this is a two-variable function, and this is also a two-variable function. So what's the relationship between them? Okay, starting from this definition, what is the relationship between capital F and small p? This is going to be something interesting, and I will leave you to think about this. Okay? And before we march into the technical detail, this is already something challenging because now we have many probability functions. And we better understand what do we mean before we move on. We have random variable x, we have random variable y, so of course we have their probability distribution function, right? And we have x, y happen together, so we have pxy. So how are they related together? Well, the thing is that you sort of imagine that on this xy plane, if you plot out all possible x and y, let's say that it expands a rectangle like what I just described. So this is the pxy that I'm talking about. And from there, you can actually derive other things. So what exactly is py? Py is the probability, the random variable, the y, take on the value y, okay? And disregard all other possibilities for the other random variable x. So what does that mean? That means that taking this y and then integrating out all possible x. So starting from pxy, if you do a partial trace or a partial integration, okay, this is called partial trace in quantum mechanics. So sometimes you will also see some other people do that. And so if you do the partial integration, and then you get a function py. On the other hand, what is px? Px is the probability for x for the random variable capital X to be particular value x. So it's a sum over all possible scenarios for different y's with exactly the same x. So the x is fixed, and then you're just integrating out all y's. And what does that mean? It just means that you integrate over this line here. And in data science, because the way that you get y and get x is really scanned through like that, and it's basically determined by the margins. And so this px and py's sometimes with respect to pxy is also called marginal probabilities. And finally, a very important concept is called conditional probability, which we explained last week in describing the Chapman equation or also the Markov chain. Okay, so the conditional probability is defined this way: in the occasion that x equal to x, what is the probability of y? And so that probability turns out to be pxy divided by px. That is, you're just picking up the pxy, the probability of pxy, and because you already assumed that x happens, so then you just divide it by px. And this conditional probability, let me emphasize one more time, that x here then acts as a parameter, right? It's the condition you set in, so it's a parameter. It's truly that this capital Y here is the random variables. And so you can actually check whether you get a probability or not. A conditional probability is still a probability. It's just that you set the parameter in a very specific way. And so if you integrate over all y, you got an expression like this, okay? And if you look at this expression, aha, that's just px. So if you divide it by px, that's 1. So great. You are all set. So I hope that this very simple yet inspiring figure help you to realize what's the meanings of probability px, py, and pxy. Okay. Oh, there's some. Ready? Let me switch back and address this. This can be serious issue. OK， 下课时间，所以乌鸦先说有一个固定频率的 pulse 声音，像是方向灯。That's interesting， 很像是背景下有节拍的声音。这里测起来大概是120赫兹，我猜是某种有用台电交流电的讯号。感谢大家。其实，在听的时候，我知道，其实，在直播的时候，最令人痛恨的，其实就是有一些固定频率的声音，其实真的是蛮麻烦的。但，我真的没有听到，所以是所有的人都有听到这个神奇的声音吗？当然了，我现在电脑是在充电了 ，so in principle you got some 120 Hz signal 也不是没有可能的事情。这样，大家继续再听听看，如果有的话，再回馈给我。那我也会上 YouTube， 因为刚刚我其实就看一下我们上一段的话，好像讯号都还好，因为我目前后端监控这边的话，其实好像都没有什么状况耶，所以我再想想看，对，目前好像都没有什么状况，好吧 ？OK， 所以那个听起来像时钟滴答声哦，那是我家的时钟的滴答声，这样哦，那个倒是真的，但那个不是120赫兹这样。背景底下有节拍器，你们听到哒哒哒哒哒哒，那是英国来的古董的钟的声音，这样，对，这是我们家的一部分，下次有机会再介绍给大家知道。如果是这个的话，那可能就还好，这个会很困扰大家吗？OK， so now I'm going back to our learning materials. I found this transition rather interesting, coming back to the chatting mode.And then going back to the learning mode. So great. Okay. So let's come back to the learning mode. I hope you sort of get some idea about the px, py, and pxy. Then we will move on since now we have two random variables. And one important thing is covariance. So the covariance is defined in the following ways. The covariance has a simple definition, that is x times y average minus x average and y average. And this might sound, why would I do that? So it's like, okay, you multiply them together and taking the average, subtract the average and multiply them together. It's almost like testing the quantum mechanics, right? You get two actions. One is a product, the second is taking average. And you reverse the order to see the differences. But you see that once you define it this way, it's truly, this is more inspiring. That is, you define delta x, which is x minus the average value. And delta y, that is y minus, there's y here, is y minus average values. And so this is the deviation from the mean. So we are basically, the covariance is trying to find the correlation between these deviations. If they are not related, then if delta x positive, delta y can be positive or negative. But if they somehow related, when delta x is positive, delta y is also positive. When delta x is negative, then delta y might also be negative. Or it can be the other way around. When delta x positive, then delta y is negative. And they are out of phase, like this. And that's why the notion of covariance is important. Because the covariance is a measure of correlations between fluctuations delta x and delta y. And because it's indicators for fluctuations, so it doesn't really matter that how you shift your data, you know? And so here, as a straightforward exercise, if you just shift x to C1, y to C2, and of course that you change the means. But don't forget, this delta x and delta y remain constant. Well, it's the same, right? It's constant shift. So the random variable is shift by the constant. The mean also shift by the constant. So the fluctuation doesn't change. And so it does not change the covariance at all. So here you see, typically when we send out some signals, there are some average values, and there is a fluctuation associated with that. And so the covariance is measuring the relationship between the fluctuations. So it won't be affected by the signal itself. That is, it does not depend on the constant or does not depend on the mean. It's an independent measures for the statistical noise. Okay, and once you define that, and these are the 4 important properties for covariance, I hope that you can check. First of all, if you just change this y to x, there's x to x, and it turns out the covariance between x and x is nothing but the variance. Okay, and covariance xy is covariance yx because you multiply them together. And also, if you scale the cx by a constant c, the covariance is also scaled by a constant c. Okay, and the final one, if you are measuring the covariance between x and y plus z, it's the same as the covariance xy and the covariance x and z. In fact, if you check all this, you find out the covariance is actually very similar to the inner products between two vectors. Okay, so the algebra is really relatively similar to each other. So that is the covariant part. So that's a very interesting good concept. Here I'm going to give you a very interesting examples. While I was writing this, I laughed quite a lot. I hope you enjoy this example. The example can be important for you. So wake up and listen to this one. We're going to talk about 2 correlated random variables, x and y. The first one is important. The first one is a binary one. Okay, it's a Bernoulli random variables. That is, you have some probability to pass this course, the math physics. Okay, and that's called x equal to 1. And if you fail, that's called x equal to 0. And the probability that you will pass this is p. And of course, then the probability you will fail is 1 minus p. Fair enough, right? So that's the first one. What about the second one? The second one, suppose now you have a partner, if you, either your boyfriend or girlfriend, okay, suppose you have a partner, and who is encouraging you to study harder. So he or she make up her mind or his mind that if you fail the course, well, it will just she will just break up the relationship with you. On the other hand, if you pass this course, then she will seriously consider whether she will continue the romance with you or not. Okay, so this then is a very interesting coupled random variables, right? So let me explain and elaborate a little bit more. That is that if you fail on the assumption that x equal to 0, the probability of y equal to 0 is 1. That means that he or she will definitely break up with you. And that also means that once you fail, it's impossible that he or she will continue your intimate relationship. Wow, that sounds like a very serious issues, right? But on the other hand, if you pass the course, then there is a chance Q that he or she will continue the relationship with you. So that's Q. And if you pass the course, and of course, since this is Q, so this is 1 minus Q. Okay? So you see these very interesting situations that how you actually analyze this whole things. And also, please, yes, we do understand we have two correlated random variable, x and y. So you might think that we have 4 possibilities and these possibilities add up to 1. It is not. If you add it up, you got 2. Okay. So that is the confusion that I already told you before. When we deal with conditional probabilities, you are really dealing with just one random variable, right? So it doesn't work this way. Be careful. And so I'm basically explaining everything here that this x and y are somehow combined together. And so you got all this pretty cute conditional probability and also the driving probability of the probability to pass the mathematical physics or not. And so let's try to calculate some of the fun stuff. Okay. Let's try to calculate how the x, y are correlated. That is their covariance. And so thus you need to calculate the xy average, x average, and the y expectation value. And so for the xy's, there are 4 possibilities. First of all, if you pass, so let's P, and she remains, okay, this Q, so P times Q, 1, x times 1, great. And for other cases, it's all 0. And here I listed other cases, and so you can go through, but then basically this is the only term you got, so that's PQ. So what about the expectation value of x? The expectation value of x is again very simple. That is, you pass the course, x equal to 1, right? And it contains 2 scenarios. That is 1 equal to 1 and 1 equal to 0. And if you add it up, well, that's also 1. So then you got P. So this is also reasonable. And finally, what is the expectation of y? Y can take on 0 or 1. So you got to be really, really careful. But since here, if x equal to 0, y is always 0, so that part is 0. So the only way that you can get a non-zero value of y is that by passing the mathematical physics. So then that's q times p. So y average again is q times p. So you got these 3 terms. Simple. Okay. Fun part comes. Covariance is this xy minus x times y. Okay, so it's xy pq minus multiply these 2 together. And finally you got this one. Q times p times y minus p. Looks familiar, right? This is the form that we encountered in previous part. And hopefully now we have a better understanding of this whole thing. So when does this covariance equal 0? Well, if you look at this, there are 3 scenarios. The first one is q equals 0. So then the covariance is 0. And the second thing is that p equal to 0 or 1. P equal to 0 or 1. P equal to 0 or 1. So try to remember one important thing. If x, y are independent, as later we will show, the covariance is 0. But in some cases, in this particular case, we know x and y are deeply coupled together. They are not independent events. But still, there are cases that the covariance can be 0. Why? Because when x or y, one of x or y becomes not random at all, it becomes definite, then there is no fluctuation. And thus, because the covariance is the product of the fluctuations. If one of the fluctuation is 0, then this whole thing is gone. So remember one important thing. when covariance is 0, it might have two completely opposite meanings. One thing is that maybe that delta x and delta y are independent, which means that x and y are independent random variable. Or it just means that delta x is equal to 0, delta y equal to 0. And it's in this case here, when q equals 0, what exactly does that mean? It's a really sad thing. It just means that your partner wants to break up anyway. So it doesn't matter whether you pass the math physics or not. And so that's q equals 0. And there's no fluctuation, right? Because delta y is 0. And also, there's in another case, the fluctuation is also 0. The covariance is also 0. That is when p equals 0 or p equals 1. I know the consequences are rather different, but statistically they're corresponding to the same covariance. That is either your grade basically is determined already. So either you pass or you failed, and there is no fluctuation. In both cases, even though the consequences are different, okay, in one case, passed, failed, but in terms of fluctuations, so the pass or fails, that's the mean, you know, and in terms of fluctuations, they're the same. There's no fluctuations. So in this very simple cubed correlated random variables, so you can start to see, sort of dig up a little bit deeper about the meaning of covariance. Okay. So now, inspired by covariance, we want to ask, in what circumference where x and y are still fluctuating, but somehow, magically, the covariance between them is 0? Well, it turns out that is what we call the independent random variables. So let me just write this down for you. When we say that x and y are independent random variable, if and only if, okay, so this is mutual, the probability of x, y is nothing but the product of probability x times probability y. So it's just pxy equal to px times py. And once you know that, we find the expectation value decoupled. For instance, you want to calculate this, right? You want to calculate the fx and g of y. And according to the definition, you multiply with pxy. But because this pxy can be written as px times py, so then you can separate the integrals into this part times this part. And this is the expectation value of f of x, and this is the expectation value of g of y. And so you see that the expectation value of the products is basically then become the product of the expectation values. So that means the expectation value is decoupled. And once you got to this point, we can then find out the covariance variances. Why? This is just a very simple special case, right? Because this x, y times together, calculating the average value, can be decoupled. So it can be decoupled. And then it just cancels the second term. So it's always 0. But let me emphasize one more time. So when you analyze the data and then you found the covariance between two random variables is 0, it's mainly coming from two possible scenarios. The first one is that x and y are independent random variables. That's great. But the second scenario, which is also very often, that is one of the random variable is not random anymore. Okay, that is in specific limit that become deterministic. And so in that sense, then the covariance is 0. And sometimes you need to look further at which one is making the covariance 0. But in any case, when you have two random variables, it's always inspiring to calculate the covariance between them to check how they depend on each other. And these will give you really important informations. Okay? Oakley dokley. Once that is done, then that's just try to march on. So we're talking about two variables, right? And so you have the t, x, y, and so then if you trace out in different directions, you get two different marginal probability, and that's closely related to the conditional probability. And also, we found out that if you have x and y, you can calculate the covariance and then see how they are coupled together. Now, we're going to do something else. We're going to consider a composite random variables. And composite random variable can take many different forms. And here I'm going to just take a very simple form. That is, suppose now I have n random variable. I just sum them all up. And so then you get a composite random variables. And to characterize a random variables, the minimum information we need is first compute the expectation value. The second one is compute the variance. And of course, then the expectation value and the variance should be related to xi. And so it is actually straightforward that if you try to compute the expectation value of this composite random variable like this, okay, and these are linear sums, so you can decompose them. So it turns out it's just basically summing over all individual random variables. This is easy. And for variance, it turns out it also works, but since variance contains quadratic term, right? So this result is not that trivial. So I may be slightly more careful and show you how this can be done. Okay, so when does this happen? It requires some things. Okay, when you try to calculate the variance of x, that's a covariance of xx. So that's a covariance summation of this, summation of this. And note that we are dealing with this x1 to xn, and these xi's are independent. What does that mean? That means the covariance between xi and xj are 0, except the I and j equal to each other. And so then this terms, when you put this summation out, the only non-zero term is delta ij, that is I equal to j. And when I equal to j, this is just a covariance xi. That's a variance of xi. So this is variance of xi, and this delta ij kill one summation. And so then you end up with just summation over I from 1 to n. And so this is a little bit surprising and actually very useful. That is, if you just sum up n independent random variables, the composite random variable, the variance of the composite random variable is nothing but the sum of individual variance. Okay, so once you prove that, then you can use this a lot. So let me try to see that why this notion of composite random variable is useful. So let's consider an interesting case. At a party, there's n people. They just throw their heads together into a pile in the center of the room. So the heads are mixed up, and each person just randomly select once. And if I ask you, what is the expectation value of people finding their own head? That is the right head. Wow, this, if you don't know how to proceed, this can get very complicated, right? Because the first person can pick up like the n-1 people's heads and everything, and you need to compute lots of combinations, and then you need to compute the probability associated with that. So it seems this is a relatively difficult question. But if you have the notion of random variable, you get the idea of composite random variable, this problem then becomes relatively simple. That is, introduce a composite random variable like this one, that's x1 plus xn. So one is xi. Xi is the ith person finding the right head. So you don't care, as long as you got the wrong head, you don't care, you just set it equal to otherwise and 0. Right? Because you're just finding the expectation values of the people finding their own head. And so the ith person got the right hat that corresponding xi equal to 1, otherwise it's 0. And this is a contribution from the first people, so you can give the head count 1 or give 0, and you just sum it all up, then that is the answer you want. And what is the probability for xi equal to 1? This problem then becomes trivial, isn't it? You got a pair of mixed-up heads, so there are n heads. So the probability you'll pick up the right head is 1 over n. And the probability works equally well for any people. So the expectation value of xi is 1 over n. So the expectation value of x is summation of all individual expectation. And you sum it up, this is 1 over n, sum over n, cancel it out, it's 1. It's independent of n. So that's the fun part. So it doesn't really depend on the size of the crowd. The expected number of people finding the right head is always 1. When the group is larger, the probability is diluted, but you have more people, so they cancel out. When the party is smaller, the probability to find the right head is larger, but you have fewer people, so then they compromise and eventually still give you 1. So that's the fun idea, that once you find the right random variables, the problems can be easily solved. So you see here, the most challenging part is actually try to write this down as the right random variable to solve the problem. Okay? With that said, can we also do the same thing for diffusion? The answer is yes, you can. So that's just revisit diffusion, but right now with a slightly different twist. So I'm plotting this in 2D because it's more beautiful. In 1D, it's always in one dimension. I try to draw that, somehow it looks really ugly. So the idea is that Brownian motion is due to random collisions, right? So in 2D, then you have beautiful pattern like this, but then we are considering 1D. So how do we do that? Very simple. Suppose now within time t, right? There are n collisions. So this n is t divided by delta t, and delta t is a microscopic time scale. And so starting from the point x0, ending up the location xn, so the displacement delta x is a random variable, right? So the delta x has nothing to do with the fluctuation, the standard deviation, everything. No. It's really just the final location minus the initial location and the difference between them. It's our good old friends when you learn the Newtonian mechanics, delta x, displacement. So this delta x is a random variable. But with these microscopic scales, collisions, this random variable can be viewed as a composite random variables. How? Well, simple. At each time step, it has different positions, right? So if you just calculated this delta, this delta, this delta, and this delta, it's straightforward to show that delta xn minus 1, delta x2, delta x1 add up to delta x. Basically, you add up all the displacements between different collision time, and then you will get the final displacement. So this is an identity. And if the collisions are effective enough. So what is collision? Collision is basically you incident with some velocity and then you change it to another velocity. And if this is effective enough, no matter what kind of velocity comes in, the outgoing velocity distribution would always be the same. Okay, in the simplest case, it's isotropic, but it is not necessary to be so. But as long as this is efficient enough, all this delta xi, that is the displacement in one duration and the displacement in next duration, so they are not related to each other. Okay, So this is the short memory assumption, which actually works in many cases. And so if these delta xi are independent, then we are at good hands. Basically, that this displacement can be viewed as summation of many microscopic displacements, and these displacements are independent random variables. And so, just like the previous one, when we find the right random variables for the head problem, right? So the expectation value decompose, and so you can calculate it. And here we are looking for the variance. And we know that the variance can also be summation of individual variance. Okay, and since each part is the same, so you just get a factor of n. But then what is the individual variance during one collision? That's relatively simple, because the probability 1/2 give you just plus a, probability 1/2 give minus a. But a squared and minus a squared is always the same. So then you add up to a squared. So basically, this delta x1 squared average is just a squared. So finally, by understanding the diffusion problems is nothing but a sequential collision events, then you can view this displacement as a composite random variables, and thus its variance is nothing but the summation of individual variance. And so then you got this one here. And you just massage it a little bit. Know that what is this n here? This n here is the duration divided by the microscopic time, and then swapping this into a squared. This is the diffusion constant. And so then we got the variance is proportional to t. That again is the beloved Einstein formula that we found before. So now you see, the nice things about knowing the probability theory is that once you got the right handle, there are many different ways which you can derive the correct answer. And so depending on which part that you are more familiar with, you might be really getting the right answer with a really difficult path, or you can find the right concept and cut it into the right angle, and you just find the solutions immediately. Imagine just within 1, 2, 3 lines, this mysterious diffusion relations can be derived, and the breakthrough is this relation here. Is viewing the displacement vectors as a composite random variable. How cute is that? Okay, so that's basically all the things that you would basically encounter. So let me rephrase what we have learned so far. We learned that when you have x and y, you need to find the joint probability, and the joint probability, when traced off in different directions, will lead to px and py, and thus you can define the conditional probability as well. And also we find very important quantity, the covariance xy, which can help you to characterize how the fluctuations delta x and delta y are related to each other. Finally, we come to the central limit theorem, but before that, let me introduce the law of large number. So when does this apply? That is the following. Given an infinite sequence of IID, so what is IID? That's independence with identical distribution. It's basically that you have a bunch of random variable x1, x2 to infinity, and they all have the same means and variance, and they are independent to each other. And so then you can construct the means. So what do I mean by means? And that is x1, x2 plus all together divided by n, and then this n goes to infinity. And one can actually show the law of numbers. It has a weak version and strong version, and stating that how this probability converges one slightly differently, but it basically just states that when n goes to infinity, that this probability is 1. And because this probability goes to 1, that means there's no fluctuation at all. And so this is the famous law of large numbers. That is, if you have a bunch of IID, the independent with identical distribution, okay, random variables, that means that x1, x2, x3 to xn, they all share the same mean, the same variance. That is, their probability distribution functions are exactly the same, but they are independent to each other. And if you just add this random number together divided by n, you got another random number. Know that doing this is not taking average. This is not the same thing. When I say that I'm taking average x1, I'm weighting x1 with the probability it appear and then calculating that number. That is what I mean the expectation value, or sometimes called the average value of x1. But here, this x is another random number, right? Let's call this random number mean of x1, x2 to x infinity. And it's defined this way. So this x has its own probability distribution function. And its distribution function turns out to be really interesting. That is, it is 1 for x equal to mu and 0 otherwise. Wow. So this is something amazing. And so we're not going to prove this. We just try to show you that if expectation value and variance are important characteristics for random variables, and this is already something pretty interesting. One can sort of see how the law of large numbers emerge. First of all, calculate the expectation value. Okay, again, that's the summation of everything. And this 1 over n is coming from, because I defined it this way. Okay, so it's not a sum. It's a sum then divided by 1 over n. That's important. And so this gives you n times mu, and this 1 over n cancel out, so that's still mu. And this is reasonable. Each x contribute means of mu's, and you have n of them divided by n, so they cancel out. You got mu. So this is almost by design. Okay, great. But what about the variance? The variance is more tricky. The variance is because you can then calculate the covariance of x and x. And because then each x contains 1 over n, so you prove that out, then you got 1 over n squared, and you got this familiar form again, this covariance xi, xj. But then xi and xj's are independent random variables, right? So you get delta ij and then just covariance xi, that's sigma squared. Okay, so you get this. And so that kills one summation over j. And so this after summation give you n sigma squared. But you have 1 over n squared. After canceling this n, you still get 1 over n. And as long as sigma squared, it's fine. It's a well-defined regular. And when n goes to infinity, then it goes to 0. And just ask yourself, if you have a probability that its mean is mu, and there's no fluctuation, what does that mean? For a physicist, I think it's good enough that it means that this x mu's always appear without any statistical fluctuations. But then in terms of mathematics, of course, things are more complicated because they would care about how this occurs along the way when you're taking the n goes to infinity. So that's the larger number, okay? And it's Q, but this is not the most useful form. So there are improvements that one can do when you do that. So then they come to the central limit theorems. That is how you can map this sort of IID random variables into a universal distribution functions. So how can we do that? Well, again, this part is completely the same, that we are given an infinite sequence of IID. That means they are independent with identical distributions, random variable x1 to xn, and all share the same mu, all share the same sigma square, but they are independent to each other. Now, let's define the shifted random variables. First of all, because these has means, so then I just subtract them, minus and mu. Second thing, don't ask me why, later you will see that I'm dividing with a square root n, not 1 over n, and also a sigma here. And so the central limit theorem shows the probability functions for x is going to be this Gaussian distribution with unity variance and zero means. Very, very standard. So again, let's see how we can understand this whole thing. First of all, how we can understand the central limit theorem? Well, let's just compute the expectation value. Okay, so the expectation value is just summing all up and subtract the constant shift and mu. So not surprisingly, when you compute this gives you n mu minus n mu, that's 0. Excellent. What about the variance? Well, the variance is, again, the same, because it's divided with 1 over square root n sigma, so both contain this. So this squared it, you get a prefactor that's 1 over n sigma squared, and the covariance of this form. But we have calculated this before, so I'm not going to repeat it one more time. This gives you a delta ij, K1 sum, and then thus you get n and sigma squared. So it's got n sigma squared, 1 over n sigma squared, cancel out, so then you got 1. So this then corresponding to a very simple probability distribution, that this E is 0 and this variance is 1. And with this, it's a good guess that you would just get the Gaussian. And in order to really show that it is a Gaussian, of course, it's more tedious, but the basic idea is more or less the same. And if you don't really care about the mathematical beauties, you can just calculate the nth cumulative motions. Yeah, you can calculate basically higher model and expectation values, and you found that agree with the Gaussian, and thus it's a Gaussian distribution. So as a scientist, what you're really curious about is really not to prove this whole thing. It's more about why we divide it by square root n. Okay, minus n mu will bring everything back to 0 mean. I think that part is trivial, right? You just distribute it and then use an x1 minus mu, x2 minus mu, and xn minus mu, and all these will be 0 mean. And so when you sum it all up, that of course is still 0 means. It is more about the variance, how the variance changes. So one Q-part of a composite random variable is if you have IIDs x1 to xn and you sum them all up, the variance of this summation grows as n. That means their standard deviation grows as square root n. And so that is why then you divide it with square root n sigma. That is the standard, anticipated standard deviation to make the standard deviation 1. And thus the variance is 1 as well. Okay. And so the reason why you can do that is really because all these random variables are independent to each other. And this square root dependence also explains why the standard deviation of x in diffusion is square root t as well. So they all origin from the same statistical mechanism. So it is that beautiful. So that is the central limit theorem. So let's see whether we can apply this, let's say, to binomial distributions. So here is the example. And so suppose now I'm flipping coins and equal to 40 times, lots of time, right? And I want to ask, what is the probability x equal to 20? And so please do not use the wrong theorems. You might think, oh, since I'm throwing this the coin 40 times, right? According to the law of large numbers, so the means will become like 20 is like approaching 1. And so you might think that this probability is approaching 1. That's a completely wrong concept. Okay, that's a completely wrong concept. Please be really, really careful. So the correct way is the following. So first of all, we start with the binomial distributions, and we want to make a continuous approximation. So this is a discrete binomial random variable with x equal to 20. And we want to find whether we can find another probability distribution function which is continuous. And they're more or less the same. So how can you do that? Well, because the adjacent interval is 1, so then we just cut this, basically calculating this probability that x is larger than 19.5, smaller than 20.5, and see how it goes. Well, then making use of n equal to 40, mu is 1/2, is 1/0. So the absolute value is fair count. So it's 1/2, and you can calculate the sigma is also 1/2. And with that, we can reintroduce this canonical random variable that is square root n sigma x minus n mu, and so you end up with this. And transforming into this y here, and noting that for this standard exponential, we can define its cumulative functions, and its cumulative functions can be calculated basically just by the area here, that's phi, okay? And so this is nothing but this y, but then it's between this smaller value to this larger value, and since we calculated, so this probability is nothing but the cumulative functions at 0.16 dot 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 minus 0.16 dot dot dot. And if you just look at the figure here, that is this one, subtract this one. So that is the area that we are looking for. But from this figure, of course, we know it's symmetrical around 0, right? So then you got, if you integrate from here to here, and if you integrate from here to here, that actually adds up to 1. So you got this very simple relation that the phi b and phi minus b equal to 1. So you can replacing this by this equation, and so then you got this can be re-expressed as 2 times phi 0.16 minus 1. Okay, so just look up this phi either on internet, or you can plug into a mathematical program, and then you get the value of 0.1272. And if you really compare with the exact result, which is the C 40/20 and 1/2 40 times, and that after calculation, it's 0.1268. Very close, right? It's very close. This estimate is really, really good. So that means that even though a binomial distribution, the binomial distribution is a discrete random variable, and the normal distribution is a continuous random variable. But as long as you feel comfortable with this approximation, okay, and then you will find it's a pretty good estimate. It's a pretty good estimate. So try to go back and digest one more time that why we need the central limit theorem here, but it actually appears that you might think that I'm throwing 40 times, and so 40 is enough, right? So you might thought the probability that it shows up with 20 heads up and 20 heads down should be significant, but it is not. It's basically just 12%, slightly more than 12%, just less than 13%. Why is that? Isn't that like half configuration is the most probable outcome? If you throw this coins more and more time, and you can actually convince yourself. If you then throw the coins more and more time, for instance, if you are throwing it like 200 times and asking the probability that 100 times that you find the heads up, it's going to be even smaller than the number that I'm calculating here. So it's never going to go to the anticipated unities as stated in the law of large numbers. So when using the law of large numbers or using the central limit theorem, be really careful. But behind this, as a physicist, I usually do not think this way. So instead of using like summing x1 to xn divided by n, or summing x1 to xn divided by square root n, I would just sum everything up, and just total sum. And just remember one important thing, starting from this whole thing, the half width will grow, not as n, but as square root n. And because of that, if you divide it by n, then you get 1 over square root n, which eventually goes to 0. And if you just didn't do any divisions in some of the thermal statistical physics, it's the total sums, then it actually diverges with square root n. Only when you are smart enough, knowing that the standard deviation scale with square root n sigma, and you divide it by square root n sigma, and then you will always get unities standard deviation. Okay, so that is the central limit theorem that I would like to share with you. And finally, I would end my videos today here with a big puzzles. So the puzzle is then, why binomial turn into bosons? The binomial random variables, as you know, look like this, right? And so I have showed you, I hope that I have showed you that after proper shift and scaling, it becomes a normal distribution. But then how come it can turn into Poisson distribution, as we learned before? It is implied that somehow Poisson distribution is the same as normal distribution, and we know the answer is definitely no, right? If this is true, why would you have a Poisson distribution at the very beginning? So what exactly does that mean? So why can binomials turn into Poisson or turn into Gaussian? And so how can both be right? So what's the relationship between Poisson distribution and normal distribution? Does this somehow imply as long as capital N is large enough, the binomial distribution will become Poisson distribution and is also well approximated by normal distribution? Is that right? Is that the law of large number? When n is large enough, there is no distinction between binomial distribution or Poisson distribution or normal distributions. Okay, so that's all the learning material I would like to share with you today. 好，那我希望大家其实在今天上课的话呢，就有学到这一些有趣的东西，这样。那我可能准备的东西有点太多了，所以我今天上课的整个长度的话，比我当初想象的稍稍要长一点点。那我会再稍稍修正一下，让大家可能其实借由 YouTube Live 来上课的话，不会这么的累。那我想时间也差不多了，所以我今天直播呢就到这边为止。那再一次跟大家讲， 这样的一个聊天室里面的讯息的话，经过一些时间的重组，它其实还会再出来。那大家其实如果对于 video， 就是说影片里面有一些东西，想要讨论的话，也可以直接在 YouTube 上面留言。那其实我或者是助教，都会及时的给大家一些回应。这样，那我们今天就直播到这边为止了。谢谢大家的参与。